Good morning, everyone. Today we're talking about exercise 4. Um, Before we begin, if you have any questions, please ask them in the chat or you can turn on the microphone. If you don't have any questions, then we can just go directly into the exercise. Okay. Uh, so today, for the first task, the historical student enrollments at Alabama University are given in the file alabama.txt containing the year and the number of students enrolled in that year. Fit a linear regression model with the least squared method on this data, predicting number of enrolled students and with the year. Okay, let's first take a look at the data that we're given. As it's described, on the first column, we have the years, and on the second column, we have the number of enrolled students. So our goal is to fit a linear regression model and then plot the data and regression line in the same plot. And then we answer the question, what is the predicted number of students for the year 2050 according to the model. Then we should look at the example images in slide and answer the question, would linear regression be a good choice for time series models? Time series data do not use existing implementation. So the goal is to implement a linear regression model ourselves. And the lecture slides for prediction are already on the eLearn page. So you can reference that as well. Okay, first let's import the libraries we need. We need NumPy and Matplotlib. Then we need to load the data. And then we store them in different variables. So the years, we select everything in the first column. Then for enrollments, we select everything on the second column. You can take a look at them. And then for the linear regression model, the formula, you can find the implementation in the lecture slides. This is the linear regression model. I think it has already been discussed during the lectures. So we're just gonna go through them very, very, very simply. Has anyone had any recommendations for advanced NumPy tutorials or other helpful stuff? Yeah, If anyone has any recommendations, they can answer this question in the chat. But I also I recommend if you want more advanced NumPy tutorials, first check the documentation, and second, there are many YouTube videos available. But the documentation is very important. They have the newest method, the newest implement ways to implement. But if other people have better suggestions, they can answer this in the chat. And we'll go through the linear regression model very quickly. Um, here are the formula for the linear regression models. Um, so in the general form, it's a straight in the general form, y equals to w0 plus wy multiplied by x. Y here is the dependent variable. So it's what we want to y is what we want to predict. So in our case, it will be the enrollment data, and x is the independent variable where we use to make uh, the prediction. In our case, it's the years, and W1 is the slope of the line. So it represents the change in Y for a 1 unit increase in X. And W0 is the Y-intercept. So it represents the predicted value of Y when when the value of X is 0. Okay, so for our formula, we first need to define W1 and W0. And how and the way to define W1 and W0. Okay, this is how we define W1. And let's define W0 as well. Okay, now let's take a look at how we define W1 and W0. So the years mean and the years mean and the enrollments mean, these are very straightforward. So they are just the average value of all the years and all the enrollments number. So we call them X bar and Y bar. So we can see the linear regression method here. We call them X bar and Y bar. It means the X with the little line above it. So years minus years mean. We are calculating the deviation of each individual year from the average year. So that's why it's xi minus x bar. So it's basically telling us how far each year is from the center of the data. And here enrollments minus enrollments mean are basically doing the same thing. These are calculating the deviation of each corresponding enrollment number from the average enrollment, which is y minus y bar. And then we multiply the result. Like here, we are multiplying the result of the deviation of a year by the deviation of its corresponding enrollment. And this is done for every data point. So we can imagine if a year that is above average and its enrollment is also above average, then the product will be positive. But if a year is below average and its enrollment is also below average, then the product is also positive. So if one is above average and the other is below, then the product is negative. Then we sum up, you can see the numerator here, which is here, the numerator part. We sum up all the products calculated before across all data points. And the sum is closely related to the covariance between years and enrollments. So it's measuring how much the years and the enrollments tend to vary together. A positive values suggests that as the year increases, the enrollments also increase. And this part, years minus years mean to the power of 2. This part are calculating the squared deviation of each year from the average year. So squaring ensures all values are positive, so they are not negative after squaring. So it gives more weight. It gives more weight to the points that are further from the mean. And then we sum up which is the denominator here. We sum up all the square deviations calculated earlier. And thus this sum is very closely related to the variance of the years. So it's measuring the spread of the dispersion of the year data around this mean. And then we divide them, the division. We divide the measure of how X and Y vary together. We divide them by the measure of how X varies by itself. So basically, this formula is telling you the W1 formula is telling you on average how many units enrollments change for a 1 unit change in years. And then to the W0 part, which we have mentioned before, W0 is the y-intercept. And it is W0 is calculated by taking the average of y value and then adjusting it based on the average x value, which is the year's mean here. This is the average x value. And um, So this ensures the line is correctly positioned vertically to pass through the center of the data cloud. Okay, this is the formula and this is how we implemented them. So then we want to draw our regression line because here the task is to plot the data and the regression line in the same plot. So for our plot, we first want to define a linear space and we call them X range. Okay, instead of calculating the predicted enrollment for a specific year, we're creating a smooth range of 100 years values that's spanning from the entire period that's covered in our data, which is from the smallest years to the biggest year. So we can this so we when when we plot the regression equation, we get a nice straight line covering the extent of our original data that we imported here. Then we can start creating figures. The first plot we're gonna add to the figure is years. The x the x the x-axis will be years and the y-axis will be enrollments. Then we need to plot the regression line. And we can add a title. And then we show the plot. You see how the formula we use here are used for predicting the y value, which is the formula we have used here, x0 plus xy that's multiplied by x. Yeah, that's how we visualize the data and we fitted a linear regression model here. Next, we need to, what is the predicted number of students for year 2050 according to this model? So to predict, we use the same formula. So we can just print out directly prediction for 2050. And we use the formula W0 plus W1, and we multiply it by 2050. So the prediction for year 2050 is around 32,000 enrollments using the linear regression model. And then we should look at example images in slide 10 to 11 in prediction. Would linear regression be a good choice for modeling this time series? Let's take a look at the lecture slides. We can see both of these plots, these time series plots, they have a lot, they vary from year to year or from time to time. They have, and the variance is very high. Oops, I think the connection dropped. Uh, we were looking at the lecture slides, and we can see both of these plots, those time series data. They vary from year to year or from month to month. And same as the data we have here. So linear regression would not be a good choice for modeling these specific data because they have too much variance, and the linear regression model cannot capture the upward and downward trend of what's happening here. For example, we have a dip here, and the linear regression model is just a straight line. It cannot capture the nuance of the data. If something happens, if you plot a linear regression model here, a linear regression line here, it's also it's just a straight line. You will lose all these nuances that's present in the time series data. So to answer this question, it would not be a good choice. And that's why for our second task, we are implementing a fuzzy prediction system using the simplified SONS method. And we use the same data, but we use a different prediction method. And the implementation of the prediction method is also has also been discussed during lectures, and the exact steps are actually here. Here are the exact steps, and all the formulas you need are in the lecture slides. So let's go to page 17. So here are some introductions of fuzzy time series prediction. And if you need, you can reference them if you need. But now let's follow the guide here and implement our fuzzy prediction system. We need to create equally spaced triangular fuzzy sets over range of number of enrollments. And then we fuzzify historic data where each year's enrollment belongs to a fuzzy set with the highest membership values. And then we create prediction rules as is discussed here. We create each fuzzy prediction rule should only have one precedent and one consequence. So the rules is similar to the fuzzy membership functions that we have discussed before. So if A1, then A2. If A2, then A2 or A3. If there are multiple consequences, combine them with the OR operation. For each, so we will create prediction rules similar to that. For each year in historical data, we need to predict the next year's enrollments using COA for defuzzification. And then we plot these predictions and original data alongside each other. and then we will discuss it. We will discuss whether the prediction is good or not. And then we have to try a number, we try different number of fuzzy sets in the original step to find good prediction results. And what happens if the number of sets are too high or too low? We will experiment with them too. The first step for the implementation, we need to set the number of sets. So this is let's give it 5 then to start. This simply is the variable that determines how many fuzzy sets you want to divide your enrollment range into. So now we chose 5 sets. That will be A1, A2, A3, A4, and A5. So this is a very important parameter, but we can tune it later. For now, we have 5 fuzzy sets. Then create a equally spaced. We need to create a linear space. First, we need to find the minimum and the maximum enrollment value in our historical enrollment data so that we can define the universe of discourse. So we can define this area. Okay, now we have found the minimum and the maximum values. Then we define we have basically found the universe of discourse here. Next, we define the fuzzy edges. Um, so now you're probably very familiar with linear space. So it starts from the minimal value to the maximum value. Then the step is number of sets plus 2. And why are we adding a 2 here to the why are we adding a 2 to the sets here? Because for example, you can take a look at the universe of discourse here. For an n triangular fuzzy sets that's placed side by side, like in the lecture here, we need n plus 2 points to define them fully. So let's let's take a look at this graph. So now we have defined we have here we defined number 5, right? Yeah, we define fuzzy sets. So we have 5 triangles. Let's imagine 1, 2, 3, 4, 5. So our universe of discourse ends here. And in our universe, to define the triangles, we need 1, 2, 3, 4, 5, 6, and 7. We need a total of 7 points to define 5 triangles. And that's why we are adding a plus 2 here. And now the fuzzy edges. Now the fuzzy edges we have here holds the defining points for our five triangular sets. For example, fuzzy edges one, two fuzzy edges five are the center of our five sets, and the center here, which means the peak of the sets. And then we need to define the spacing. Since our linear space is created evenly, so they are evenly spaced points. So the difference between any two adjacent points is constant. They're the same. And so we use this line, 1, because there are, remember, the fuzzy edges stores the peak, the center of the set. So we are using this line to calculate that spacing. And the spacing is equal to half of the base width of each standard triangular fuzzy set in this construction. So basically, it will be like from here to here, or from here to here. It represents the distance from the center of a triangle to its left or right base points. So where the membership is 0. So basically, it's calculating here, 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 here. They are equally the spacing is constant, so they are the same. And then we need to calculate. Next we need to implement the fuzzification rule. Okay, let's implement the fuzzification rule. So fuzzy enrollments. And what we're doing here, we are assign enrollment to the fuzzy sets with the highest membership value. For our equally spaced triangular sets, any enrollment value will have the highest membership in the set whose center is closest to. So here, fuzzy set edges, we are selecting the center of the five fuzzy sets, and the indices go through the indices go through 1 to 5 from 7 points. Basically, it starts at index 1 and it stops at the last index, the last element in the array. But it's very important because the step index slicing is exclusive. So selecting elements from is actually selecting elements from index 1 up to, but not including the index 6. It's not including the index 6. And then the none here, we are reshaping the center array into a column vector. And after that, we are adding the fuzzy spacing. The fuzzy space, we're adding the spacing to each center point. So this is calculating the position of the right edge, where the membership drops to 0 for each fuzzy set. So we are calculating from the center to the spacing. We're calculating where it drops to membership 0. If you are following the graph. Next, we are comparing. We're comparing the results. So enrollments larger than this result. Here we're comparing each enrollment value, every single enrollment value against the right edges, against the right edge of each fuzzy set, which has been created into a column vector here. And the result from this comparison is a Boolean array that contains true or false, and the shape will be the shape is number of sets and number of years. So fuzzy enrollments that we stored here is true if enrollment is greater than the right edge of the fuzzy set I, and it is false if if the enrollment is smaller. The value of the enrollment is smaller, then it will be false. Okay, then okay, what we are doing here, remember the fuzzy enrollment here are Boolean values. So we are using the Boolean array from the step above to determine the index of the fuzzy set each enrollment belongs to. Here's very simple. We're using NumPy's argument to find the index of the minimum value along the axis. False is treated as 0 and true is treated as 1. And we are operating it on a column-wise axis. So it means for each year's enrollment. It finds the index of the first false value because false is treated as 0. So it finds the first false value that's encountered in each column. And then we are adding this. we're adding this because um we need to check the last row of the Boolean array. Here they have how many triangles? 9. They have 9 fuzzy sets, but we have 5. So we're checking the last Boolean array. Here it equals 1. So it is true if the enrollment exceeds the right edge of the very last set. And multiplied by number of sets minus 1. If true, then this part evaluates to number of sets minus 1. Otherwise, it's 0. And the purpose of this is to ensure the values that are clearly belonging to the last set. If a value here is clearly belong to the last set, but if this value has passed its center or maybe even passed its right edge, so we need to ensure those values are definitely assigned to the index number of sets. That's number of sets minus 1. So the base result here will identify the index k for the set where the membership is the highest for most cases. And this is just for one very specific edge case scenario. The result we get here. Now the fuzzy enrollments array contains is the same length at the is the same length as the original element original enrollments, and each element in this array contains an integer from 0 to the number of sets minus 1, which represent the index of the fuzzy set to which the enrollments belongs. So for example, A1, A2 is mapped as A1, A2 is mapped to 0, 1, 0, 0, 1, 2, 3, 4, and it goes on. And that's how we fuzzify historic data. And then we need to create prediction rules. First, we are initializing an empty dictionary that are named rules. So this dictionary will be storing the fuzzy transition rules, that's such as this. The keys in the dictionary will be the fuzzy set indices from the current year, which is the if part, or you can call them the antecedents. And the value associated with each key will be a set that's containing all the fuzzy set indices that were observed in the following year. And that's the then part, the consequent part. Using a set Um, and we also there are requirements here. If they are multiple consequence, we need to combine them with OR operation. But we will use a trick that we don't need to handle any OR combination because the set will naturally store a connection of unique items. First we need to loop through the indices of the fuzzy enrollment array. And we minus one here because um, we minus one here because inside the loop, we need to look at the current year, I, to end the next year, which is I plus one. And if the loop went all the way to the last index, the length will, which the length is minus one, and it will try to access fuzzy enrollments I plus one. Then it will cause an error, index out of bounds error. So we ensure we only look at the pairs of consecutive years where both years exist in the data. So we don't go to the very last one. We rename them. We are renaming them to a new array. Fuzzy my enrollment I, like we have discussed before, is the fuzzy set index that's assigned to the enrollment in the year I. And here we're retrieving the index assigned to the enrollment in the immediate following year. And then we need to build the rules. Um, Here we are building the rules. Rules get. This is a safe way to access the dictionary. So the original set, if the original set is already a key, which means that we've seen this in the current state before, it will return an existing value associated with it. And if the original set is not yet a key, so that means this is the first time we've encountered this current year. So then it will return the default value provided, which is the set function here. The set function here creates a new empty set. And then we perform a set union operation. It takes the set that are retrieved from rules get, and it adds the element next set to this set. So here the sets automatically handle duplicates because of the dictionary. So if the next set is already in the set, if the next set is already in the set, adding it, adding it again has no effect. So this basically handles the case where the same transition happens multiple times in the history. And next we need to do prediction. We initialized two empty lists. Prediction year will store the actual year number for which a prediction is made, and the enrolls will store the corresponding predicted enrollment number. And we start a loop again we start a loop again to iterate through the indices of our historic data. Then we stop one element before the end. This is because for each year I, we will predict the enrollment for the next year. So we cannot predict the year after the last year in our data set using this approach. So first inside the loop, first we add the year number to the prediction year list. And we plus one because we need to label the prediction we're about to make because it actually belongs to the next year. And then we retrieve the fuzzy set index that the enrollment for the current year I belongs to. So this will be our input to our prediction rules. So we look up fuzzy now, which is the current fuzzy state, as a key in the rules dictionary. It will retrieve the associated value, which is a set that contains the indices of all the fuzzy sets that are historically followed fuzzy null. For example, if fuzzy null is 1, which represents set A2, and if the rules is A2, if A2, then A2 or A3, then the successor would be the sets 1, 2. Okay, here, this is the first step uh, for our defuzzification. So it's translating the fuzzy output, which are successives. And successive, they are indices. So we are translating these indices, the fuzzy output, back into representative numerical values. It will iterate through each index x. Oh, for each x. For each x, it will access the fuzzy edges. And I think, do you remember that the fuzzy edges stores the defining points of the triangular sets? So fuzzy edges 1 is the peak of the set 0, and fuzzy edges 2 is the peak of set 1, and so on. So fuzzy edges x plus 1 gives the enrollment value at the peak of the fuzzy set represented by x. So the result, successive peaks, is a list of these peak enrollment values. And then we are performing the defuzzification using a centroid method approach. Like it has described here, we need to use COA for defuzzification. And to do that, we just need to calculate the mean of the numbers in the peak list. If there were only one possible successor set, the mean is just the peak of that set. But if there are multiple possible successor sets, for example, 1, 2, then the prediction is the average of their peaks. And then we append the calculated crisp, which is defuzzified numbers, to the crisp prediction, to the prediction enroll list we have initialized earlier. Okay, so now we have implemented all the steps. Now we can start plotting them. We add a figure. And we can give it a legend. Maybe you can also give it a title. Okay. We plot the prediction and the original data alongside each other. Is the prediction good? And then we need to try different number of fuzzy sets in the original step to find good prediction results. What happens if the number of sets are too low or too high? And to answer the question whether this prediction is good or not, there are a couple of ways to define how good a model is or not. Um, First, let's see if this model follows, the fuzzy prediction follows a general trend or not. So does it capture the general trend of the data? And as we can see, for our number of sets 5, it does capture the general direction or the overall trend of the original data, like reasonably. It's not too good. It's not very, very high resolution, but it does capture the trends, the ups and downs of the data. But the fuzzy prediction tends to lag a year behind the original data. So the prediction for the year I plus one, the next year is based on the state in the year I. So if there's a sudden jump in the current year, the fuzzy model, which is using this rule-based transition, cannot anticipate it. So it will only react in the next year. And that's why we see this sort of step-like behavior. The predicted line is not as smooth as the original data, and it looks like it's like a step. And this is happening because the prediction is based on the average of the peak of the successor fuzzy sets. So if the input fuzzy set remains the same for several years, but it didn't happen in our data. But generally speaking, if the input fuzzy set remains the same for several consecutive years, the predicted output value will also remain the same. And it will create this flagged, it will create a sort of a flagged segment in the prediction line, even if the original data had minor fluctuations. Because and it doesn't capture that because it's based on the average of the peaks. So to say how good this prediction is, if we're comparing it to random guessing, then this is a better model. It's good. And even if we compare to the linear regression model we have implemented earlier, like the linear regression model didn't capture the trend, the downward trend here. So even compared to this model, the fuzzy prediction model is better. But if we are comparing it to a more sophisticated forecasting model that we have now, like machine learning models um, or Meta's profit prediction model, then this is a very basic model. But the strength of the fuzzy prediction model is that it can capture the general trends and it can adapt to a range of data because it goes through this fuzzification method. So that's the discussion on whether this prediction is good or not. Um, Finally, we should try a different number of fuzzy sets in the original step and to see the different results. So remember we have a parameter here that we can tune, but we had the default value of 5. Now we can change it to a smaller result and see if see if the plotting changes or not. And here we can see when we set a number that's too low, each fuzzy set will cover a wide range of enrollment values. So the definition is low. It has a very coarse granularity many different enrollment figures got lumped together into the same category. So that's why the result we have here, it's very general. We have this trend here, but we lose most the highs and lows of the data. And this is what we call underfitting. The model is too simple to capture the underlying structure of the original data. Let's see if 3 works. Like 3 is already a lot better. But at the beginning, it's not doing so well at the beginning, but it's already a lot better than 2 sets of fuzzy sets. And now let's increase the number to 10. Let's try a higher value. And now we can see it's more nuanced. The result is much better than our original plot, which had 5 number of sets. And now let's try even higher. See, the prediction is more closely plotted to the original data line. And that means the prediction is getting better. But what if we give it 1,000 iterations, 1,000 fuzzy sets? And now we can see it's the exact line as it was before. So a higher number of fuzzy sets can improve prediction accuracy, but if we give it a too high number, each fuzzy set covers a very, very narrow of the enrollment values. So the definition is super, super high. It's a very fine find fuzzy set. So each specific historic enrollment will get its own fuzzy set or close to that if the number is high enough. And the rules becomes so specific to the observed historic sequence. So um, you get those rules that only occurred once in history. So then the predictions start to follow the previous year's actual value because it's essentially copying a copy of the original data because the prediction for the next year is based on the current year. And the map has covered all of them. The So this might look like a good prediction or a good fit on this graph. It's probably 99.9 accuracy. It looks might look like a good fit, but it's not really forecasting. It's just repeating the past. The model is memorizing the training data, so it will not generalize good it will not generalize well to actual future values because it's very now it's very, very sensitive to the noise in the historical data. And this is what we get as an overfitted model. The model fits the noise and the specific sequence of the training data too closely. So it lost its ability to generalize. Um, the So you need to experiment with different number of fuzzy sets. So I think the common value will be somewhere between 10 or 20 for a moderately sized data set that we had here. And you can increase the set if it's increase the set if it's 2 cores or it doesn't capture the trend, and you can decrease it if it looks like a exact copy or noise exact copy of the original data. So the best number should balance the trend, but it shouldn't fit the historical noise exactly. And that's a parameter you can tune. It also depends on programmers or researchers' preference. Okay, I think we covered everything in for exercise 4. We finished 2 tasks. Um, Let me know if you have any questions. And also, I think now is probably a good time to start preparing for the group presentation. If you have any interesting topic, you can post them on the forum on the eLearn page and try to find other people who are willing to join you on the same topic. But if you don't have any questions for me, then that's it for this week's exercise session. All the materials will be uploaded to eLearn later. You can find the prediction. This is the lecture slides that Professor Gao uses during lecture, and all the steps, all the formulas are here, and the recorded video of this session will also be uploaded later. Thanks to everyone who has come today, and have a good weekend. Have a good week ahead. It's Monday. Thank you.